We are now going to discuss the idea of probability distributions. Probability distributions. Okay, so in order to discuss probability distributions, let me define a random variable. A random variable is just some variable whose value depends on chance. Or you can think of it as some variable whose value cannot be predicted with certainty. Okay? So a variable whose value cannot be predicted with certainty. Okay, so kind of like a probability experiment. Any action whose outcome you can't predict with certainty. So now a random variable is going to be a variable. So if you remember, a variable is something that varies from observation to observation in your population. And you can go to, like, let me give an example, like the age of the students in this class. I could go to each one of you, and your age is going to vary from person to person. And when I observe the value of that variable, I get a piece of data. Okay, and then I could write it down and I'd have a data set. Okay, so a random variable is just a variable whose value you can't predict with certainty. So, you know, if I have any data set or any population or whatever, if I randomly select an observation from that population, then pretty much any variable could be a random variable if I can't predict with any certainty what the value is going to be. So let me give you some other examples, and let me start off with a real simple one. So consider rolling a six-sided dice. A six-sided die. Okay, and then we're going to let x equal the number rolled. So in this case, I can't predict with any certainty what the value of x is going to be. I do know that it'll be the numbers from 1 to 6. Those are the possible values of x, but I can't predict with any certainty what those values will be. So this is a random variable. And notice we'll use like a capital X to denote my random variable. So when you have a random variable, what you can do is you can make what they call a probability distribution for your variable. And basically the probability distribution lists out the possible values of your variable. So in this case 1, 2, 3, 4, 5, and 6. And then for each value, the probability distribution will give you the probability of that particular value. So 1 would be 1/6, 2 is 1/6, 3 is 1/6, 4 is 1/6, 5 is 1/6, and 6 is 1/6. Okay, so in this case, each of the values has the same probability. So what we can do is we can also construct a probability, kind of a probability distribution graph or whatever. I'll just put the values here, 1, 2, 3, 4, 5, 6. Right, these are the values of x, and they're all 1/6, so each one will go up to 1/6. So this would be the graph for this particular random variable. It kind of looks like a bed of nails or whatever, but they're all the same, and we would say that this is a uniform random variable. If all the probabilities are the same, it's a uniform random variable. Now there's one very important thing about a random variable. In order to have the true probability distribution of a random variable, all the probabilities must add up to 1. If they don't add up to 1, then you don't have a true random variable. So in this case, they do add up to 1 because I have 6 of these, right? There's a common denominator, so I add the numerators and I would get 6 over 6, right? And that's equal to 1. Okay? So in order for a probability distribution to be a true probability distribution of a random variable, the probabilities have to add up to 1. And if they don't, it could be that you've made a mistake with the probabilities, or perhaps you missed one of the values of the random variable. But they all need to add up to 1. Okay? So now, let me do another example here. So let's consider flipping 3 coins. Okay, so let's consider flipping 3 coins. And then let's let x equal the number of heads that we flip. So for example, you could get a head, and a head, like all 3 heads. That would be like x would be 3 in that case because you have 3 heads. Or maybe you get a head, a tail, and a head. That would be 2 heads. You could get a tail, and a head. That would be 1 head. Or you could get tail, tail, in which case you don't have any heads, right? So if I were to make a probability distribution here, the possible values for x would be 0, 1, 2, and 3. So there's actually 4 possible values. You could have no heads, 1 head, 2 head, or 3 heads. And so now, what about the probabilities here? So let me show you some. We're not going to do a lot with this, but one way you can find the probabilities for a situation like this is by using something called a tree diagram. And the way that I do this is I'm going to have 2 branches here representing the head or tail of the first flip of the coin. So I flip the coin, and it could either be head or tail. Okay? Now, for the second flip of the coin, I'm going to put a set of branches off of each of these. Okay? And what this is if I flip a head first, then when I flip the second coin could be a head or a tail. Okay? But if I flip a tail first, the second coin could be a head or a tail. So now, if I'm flipping 3 coins, what I'm going to do is do a set of branches off of each one of these. Like this. And each one of these would be a head or a tail as well. And so this would represent like flipping a head, and a head. Or this would be a head, and a tail. Or I could do a head, a tail, a head. Or a head, a tail, a tail. Kind of like that. So head, head. That would be one of the outcomes of the experiment. Or head, tail. That would be a second outcome. Head, tail, head. It's a third outcome. And then a head, a tail, a tail. That's a fourth outcome. Or I could do a tail, a head. So now this is a tail on the first flip, and then 2 heads. Or I could do a tail, a head, and a tail. Or I could do a tail, and a head. Or a tail, and a tail. So this would be my sample space for flipping 3 coins. And there's actually 8 outcomes in my sample space. So each one of these is an outcome. Okay? I could get all heads, 2 heads and a tail, or a head, a tail, and a head, a tail, and a tail, so on, all the way to tail, tail, tail. Okay? So this 8 outcomes in my sample space. So the bottom number of these probabilities will be 8. And for 0 heads, this is the only outcome, tail, 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 where I would get 0 heads. So this would be 1, 8. Okay, so for 1 head, there's 2, 2 right here. This would be one of the outcomes with only 1 head. Not that one, but this one has only 1 head. And this one has only 1 head. Okay, has 1 head. So 1, 2, 3. So it looks like there's 3 out of the 8 outcomes that have 1 head. So 3 eighths. And what about 2 heads? Well, you have this one, you have this one, you have that one. So it looks like there's 3. So 2 heads would be 3 over 8. And then 3 heads, this would be 3 heads. There's only 1 outcome, so 1 over 8. So this is my probability distribution for this situation. I flip 3 coins, let x equal the number of heads. Possible values of x is 0, 1, 2, and 3. And I was going to say for 0 you have 1 8, for 1 you have 3 eighths, 2 you have 3 eighths, and 3 you have 1 eighth. And if we check and make sure all of these add up to 8. 1 plus 3 plus 3 plus 1 is 8 over 8, which is equal to 1. So this is a true probability distribution. Okay? And then we can make a histogram or a diagram of this. We got these 4 outcomes, 0, 1, 2, and 3. This is x, this is p of x. And then maybe I'll do 1 8, 2 eighths, 3 eighths. 1 8, 2 eighths, 3 eighths. So 0 goes up to 1 8, 1 goes up to 3 eighths, 2 goes up to 3 eighths, and 3 goes up to 1 8. So this is my probability distribution. This is a picture of the probability distribution for this random variable. And notice it's no longer uniform, right? They're not all the same probabilities. But it is symmetrical, right? It's the same on both sides. And here's kind of the neat thing. If I draw a curve that goes through these, we actually get this nice symmetrical bell-shaped curve. And we're going to study this curve. This is a normal curve, and we're going to study that in Chapter 6. But this probability distribution, in a sense, kind of has a normal shape to it, like that. So one other thing is the probability distributions that we're looking at in this particular set of videos. These are known as discrete probability distributions because the variable is a discrete variable as opposed to a continuous variable. We're counting the number of heads or the numbers from 1 to 6 on a dice. So the variable is discrete, and these are known as discrete probability distributions. Okay?